Okay, so welcome everyone. It's a great pleasure to have someone from not too far from here, at least where I am, but okay, that doesn't mean anything these days. Francesca Arici. She will talk about SU2 symmetries in exact sequences on C-star algebras, of C-star algebras through subproduct systems.
Thank you very much, Walter. And yeah, thanks to all the organizers for the invitation to present this work here. I'm very excited about this, and I'm sorry for the very long title, but I didn't know what keywords to use. So there will be a bit of various things in this talk, and as I said in my abstract, this is also motivated from multivariate operator theory. But to begin with, I would like to just a second. Yes. Oh, sorry. Yeah. Okay. To start with a very simple example of a sister algebra, or rather of extension of sister algebras, which is the triplets extension. So I'm pretty sure that everyone that is in the audience is very familiar with this object, but I thought it would be helpful to recall this construction also in view of the construction that I will present later on in the talk. So my starting point is probably one of the easiest examples of a commutative sister algebra. Well, complex numbers are probably the easiest, but this is somehow one of the easiest. Is the circle algebra. So we're looking at S1 as points in the complex plane that have norm 1. And we consider the sister algebra continuous function on S1. And this, if you're more algebraically oriented, can be thought of as closure of a set of Laurent polynomials in a suitable norm, and which is the supremum norm. And the idea is that this sister algebra can be represented very compactly on famous Hilbert space, the Hilbert space of two-sided sequences. And the way this is represented is via multiplication operators. So but to be more precise, we can look at the space of L2 functions on S1 and identify it with the space of the little L2 of Z, so the two-sided sequences. And the isomorphism that allows us to identify these two Hilbert spaces is the Fourier transform. Under this transform, the multiplication by the function e to the 2 pi I theta is mapped to an operator which is known as the bilateral shift. This operator takes the vector en and maps it to the vector en plus 1, and it has an adjoint that does the opposite things. It takes en and maps it to en minus 1. So you see immediately from the definition that U and U star commute, and that's not surprising because we have a commutative sister algebra, and then you can define C of S1 to be the smallest C-star subalgebra of the algebra bounded operator on this little L2 that contain this unitary operator U. So this is basically just a Fourier theory and Gelfand theory combined in the slide. Now, there is another similar construction, which instead considers the Hilbert space little L2 of n, which is the space of one-sided sequences. And there we also have a shift operator that now takes the vector with label n, and so the orthonormal base vector with label n and maps it to en plus 1. This operator has an adjoint that does almost the opposite. So it's very similar to what we had before, but there's a very important difference because T star of en is en minus 1 if n is positive, strictly positive, and it's 0 otherwise. And the reason for that is that these sequences are not two-sided, they are only one-sided. We can mimic the previous construction and look at what sister algebra this operator generates. We call it the triplets algebra, and it is the smallest sister subalgebra of the algebra bounded operator on little L2 of n that contains this operator T. Now, clearly the sister algebra is not commutative because if we look at T star T and T star, the two operators do not agree. In particular, you can see from the definition that T star T is equal to the identity operator because it first shifts up and then shifts down. And T star is almost the identity operator, which is actually the identity operator minus the projection onto the kernel of T star, because T star shifts down and then T shifts up, but when T star hits E1, it maps it, when T star hits E0, it maps it to 0. So that's what it has a kernel, it's not invertible. So by looking at these two relations, T star T equal to the identity and T star is equal to 1 minus projection onto a one-dimensional subspace, we see that the elements of the C-star algebra T will commute up to compact operators, because the compact operators are a limit of finite rank operators. And in particular, we get an exact sequence of C-star algebras where we have the ideal of compact operators on L2 on little L2 of n sitting inside the Toeplitz algebra T, and then the quotient of T by the compact operator, as I said, is a commutative algebra because the elements of T commute up to compacts, and this commutative algebra is actually the algebra C of S1. Now, this is, I think, one of the most basic examples of extensions of C-star algebras, and it has so many profound consequences in the whole theory of operator algebras and in non-commutative geometry. So you can get various results from that. It induces the Noether-Goldberg-Krein index theorem. It is used in Kutz's proof of Bott periodicity. It is used in proving the existence of Pimsleur-Voiculescu exact sequences for cross products by the integers, and many more other instances. And if you want to think of what this extension is telling you from the viewpoint of non-commutative geometry, it is telling you that the algebra of continuous function of the circle is the boundary of the Toeplitz algebra. So if you want, you can think of the non-commutative algebra T that we see in the middle of this exact sequence as a non-commutative disk. And this analogy is actually there also at the level of spectra, because the spectrum of this C-star algebra is the disk. So somehow this is a non-commutative boundary extension, if you want. And it will be extensions of this form that will be discussed in the rest of my talk. So I made this slide with some extensions. So what you see on the top of this slide here is I did this Toeplitz extension, and I would like to briefly talk about two generalizations of these Toeplitz extensions, which I put on two parts of the slide. On the left, you see the extension for Kunz-Pimsleur algebras of injective C-star correspondences. I wrote the one without the injectivity assumptions, where you have an ideal which is the most general one, but I will briefly discuss a special case in a second. And the other extension that I have is Arveson's Toeplitz extension for odd-dimensional spheres, which is a generalization of the one above for higher dimensions. Now, all these extensions are examples of what is called the defining extension for Kunz-Pimsleur algebras of subproduct systems, which are objects that were introduced by Shalit and Soler in 2009, and then later studied by Wieselter in 2012, and by many more people who are probably also in the audience today in the course of the years. So let me just give you a brief recollection of what these two extensions that you see here are. So let me first go to the Kunz-Pimsleur algebra of C-star correspondences, and this what follows in the next slide should serve as a sort of motivation for my talk. See if it clicks. It doesn't click. Okay. So Kunz-Pimsleur algebras are universal C-star algebras associated to injective C-star correspondence. So they were constructed in a paper by Pimsleur in 1997. Indeed, under the assumption that the starting point was an injective C-star correspondences, and they generalize many well-known constructions in operator algebras, like cross products by the integer, also the Toeplitz extension that I talked about earlier, Kuntz algebras, Kuntz-Krieger algebras, graph C-star algebras, and many more. A special case of this construction is that when the correspondence one starts from is a self-Morita equivalence by module. So self-Morita equivalence by module is a correspondence. That means it's a Hilbert module with a left action, where the left action implements an isomorphism of the compact operators with the coefficient algebra. So in our paper that was published in 2016, which was joint work with Jens Kohn and Giovanni Landi, we showed that Kunz-Pimsleur algebras of self-equivalence by modules could be interpreted as non-commutative associative circle bundles over the coefficient algebra. And we also observed that the corresponding six-term exact sequencing K-theory that one gets from the Kunz-Pimsleur extension is a very familiar form. It only contains the K-theory group of the coefficient algebra and of the Kunz-Pimsleur algebra. And there is this map here between mapping the K-theory group of A to itself, which is the Kasparov product with the class of one, with one minus the class of the bimodule or the correspondence one starts with. And what is striking about this correspondence, about this construction, is that the correspondence between Kunz-Wimser algebras and circle bundles is not only there at the algebraic level, or if you want to, meaning that the Kunz-Wimser algebras have a structure of non-commutative circle bundle, but also the K-theory exact sequence that these algebras induce has exactly the same form as the classical Gisin sequence for circle bundles, where you have exactly the same sequence. Of course, the indices of the K groups are up, and you also have one minus the class of, in that case, of a line bundle. So this was our observation in this paper, and it's natural to wonder whether there are other generalizations of this exact sequence in higher dimensions. So part of my talk will try to address that problem, though the answer is not completely satisfactory at the moment. Oh, I see a typo here, so this will be fixed in when I send the slides to you. So let me go back to, okay, my clickers don't work. That's a bit annoying. Okay, let's go back to this slide where we have all the extensions together. So the other extension that I would like to talk about is this Arvidsson-Stiglitz extension for dimensional spheres. I'm really sorry that this doesn't work. I had prepared all nice hyperlinks. No. Okay, so the Stiglitz extension for odd sphere, as said, is a generalization of the Stiglitz extensions that we saw before. So our starting point is a fixed positive integers d, and we consider d commuting variables and consider the space of polynomials in these variables. So this is a commutative polynomials, and we use a compact notation that for every z in these variables and for every multi-index, when we write z to the power alpha, we actually mean z0 to the power alpha 0 times blah, 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 z d minus 1 to the power alpha d minus 1. Starting from the space of polynomials, we can define a Hilbert space, which is a graded Hilbert space. It's called the Drury-Arverson space, H2D. And this is a completion of the polynomials C of Z0, Zd minus 1 with respect to a particular inner product that I've written here. So the inner product between Z alpha and Z beta is almost always 0. And it's not 0 when alpha is equal, when the multi-indices alpha and beta agree. And in that case, it has this expression that contains the multi-index factorials. The reason why these coefficients appear has to do with the isomorphism that you have between homogeneous polynomials and symmetric tensor powers. Now, this Drury-Arverson space, of which the space H21, so the Hardy space is a particular case, can be identified with a space of holomorphic functions. They're the holomorphic functions on the ball, on the d-dimensional ball, which have a power series expansion of this form, which satisfies this condition, which just means that the norm coming up from the inner product is finite. As said, you can use the identification between homogeneous polynomials and symmetric powers to prove that this Hilbert space H2 of Z is isomorphic to the symmetric Fock space in the variables. So it's just a Hilbert space direct sum of symmetric powers of CD. Okay, so in some sense, this you should think of this space as generalized the Lidl L2 event that we saw in the Stiglitz extension before. And now on this space, we can consider what is called the D shift. So if we look at H2 of D as a completion of commutative polynomial, we have a D tuple of multiplication operators, one for every generator. But we can, and the way to see this multiplication is also through what is called the compression of the shift of the full Fock space. So the first observation is that the symmetric Fock space that here wrote as F-sim CD is a subset of the full Fock space, where we just take tensor powers of CD with itself in arbitrary powers and then sum them all up in the Hilbert space sense. Now, if you consider the orthonormal basis of CD, and we look at the orthogonal projection between the full Fock space, from the full Fock space onto the symmetric Fock space, then we see that we have what are called the compressor shifts. So these are given on n symmetric tensor by first concatenating with one of the basis elements and then projecting down into the symmetric part of the tensor power. And this D tuple is called the commutative D shift. And through the isomorphism that you have between the Drury-Arvidsson Hilbert space and the symmetric Fock space, which is a unitary isomorphism, we have that the D tuple of multiplication operators in the polynomial picture is mapped to these compressed shift operators. So it's very natural at this point to wonder what the sister algebra these shift operators generate becomes. And there are several properties that those operators satisfied. So when we talk about D shift, we refer to the collection of these D operators, T0, TD minus 1. The D shift is commuting, meaning that two of those entries commute. So Ti Tj is equal to Tj Ti. Then it has this property that when we sum up Ti with Ti star, we get 1 minus the projection onto a finite dimensional space or onto the vacuum vector. And this is precisely what we also have in for D equal to 1 for the unilateral shift. And then we have a condition which is essential normality, which means that the commutator of Ti star with Tj is a compact operator. And this, this is really the formula. So Ti star Tj minus Tj, Ti star is equal to 1 plus n to the minus 1 times identity operator minus Tj Ti star. And the reason why I wrote this formula is because it will be a special case of our construction, but I want to remind you about the number operator. So the number operator is the operator that takes an n tensor, an n symmetric tensor, and returns that tensor times n. So it's the familiar number operator that tells you where the tensor you're looking at lives. And if you look at 1 plus n, the minus 1, so the inverse of the operator 1 plus n, this is actually a compact operator from which it follows that the adjoint of Ti and Tj commute up to a compact operator. So the consequence is then that we have a similar extension to the one that we saw before. If we look at the sister algebra, the unit of sister algebra generated by the D shift, so by these D operators and the unit, we have an exact sequence of sister algebras where we have the algebra of compact operators on this Drury-Arvidsson space that sits inside the tuplets algebra, and the quotient is a commutative sister algebra, and this commutative sister algebra is the sister algebra of functions on a 2D minus 1 dimensional sphere. So again, you can think in analogy to what I said before, and consider this tuplets algebra as some non-commutative ball in some sense. Or if you want, you can see the 2D minus 1 dimensional sphere as the boundary of this tuplets algebra, whatever that means. Okay, I'm going back to the motivation. So now that I showed you these two examples, I would like to stress that they are all examples of a particular construction, which is that of subproduct systems of C-star correspondences. And in the rest of my talk, I'm going to talk about a very special case, which is subproduct systems of Hilbert spaces. And maybe this is a good point to ask if there were urgent questions in the meantime. Otherwise, I'll move on to the next part. I'll go on and talk about, subproduct systems of Hilbert spaces. So what I'm going to discuss now, it's based on joint work with Jens Kohl, who I think is in the audience, but I'm not sure.
I'm here.
Hi. Okay, so this construction of subproduct systems is actually much broader than what will be discussed in those slides. But for the sake of this talk, I will focus on the case of subproduct systems of Hilbert spaces. Okay, so we start from a sequence of Hilbert spaces labeled by positive integers, and we have maps that we call iota from labeled by two indices, k and m, and those go from E labeled k plus m to the balanced tensor product. Oh, sorry, that shouldn't be this B of ek with em. This is a sequence of isometries between those Hilbert spaces. And we call this collection a standard subproduct system whenever we have the following. So, okay, so there are three typos in this slide, and I cannot correct them because my iPad is not collaborating, but you should think about just standard subproduct system of Hilbert spaces. So E0 is just a complex number in our case. Then we have maps I0M that map EM to E0 tensor M, and the EM0 from EM to EM tensor E0. These are just canonical identifications. And then we have this sort of associativity condition that means that whenever we compose the identity on the Hilbert space with label K with this inclusion maps of L plus M into the tensor between EL and EM, and then we compose with this other map here, then we get the reverse arrow. So you should just think of this identity as an associative sort of associativity between our Hilbert spaces. And this is a map that goes from E to the with the label K plus L plus M to EK tensor EL tensor EM. Now we will call these isometries structure maps of our subproduct system. And this is what in the literature is called the standard subproduct system. In general, in our paper, we call it just a subproduct system, but for everything that follows now, we assume to have these particular conditions. Now, these subproduct system appear a lot in various settings, and one of the interesting settings is that they play a role in the study of algebras of polynomials in non-commutative variables. In their paper in 2009, Schlitt and Soler proved what is called the non-commutative Neutralization, and I would like to mention this as a general motivation for our work. So we look at a finite set of variables. This should be somehow remind you of the Drury-Arveson construction. But now instead of looking at commuting variables, as we did before, we consider a free monoid generated by those variables. So this free monoid is naturally graded by length. So meaning that we can decompose it over the length of words. And then we can look at the complex free associative algebra generated by this monoid. This is the algebra of polynomials in n+1 non-commuting variables, and we call an element of this algebra non-commutative polynomial. Now, because this monoid is graded by length, and this commutative, this non-commutative algebra, this free associative algebra, is also graded. So we say that a polynomial is homogeneous of degree m if it belongs to the span of xm. Now, the idea of this non-commutative Neutralization is to look at an n+1 tuple of operators acting on some Hilbert space and consider the algebra generated by such operators subject to certain polynomial relations. So we use again a multi-index notation. So if we have alpha to be a collection of words in our monoid, a length m word, then when we write t to the alpha, we actually mean the concatenation of the operators T alpha 1, T alpha k. We also use the convention that T1 is equal to the identity on our Hilbert space. And then given a complex polynomial in this non-commutative variable, we can actually say what it means to have the polynomial in this tuple of operators. And this is simply the linear combination of these operators T alpha with the same coefficients that appeared in the polynomial. Now, the reason why I'm introducing this is to do with the theorem by Schlitt and Soler, which is a correspondence between proper homogeneous ideals in the free associative algebra and standard subproduct system with the prescribed fiber. So this works in particular in the finite dimensional case, which is what we're going to study in the rest of, discuss in the rest of the talk. But to give you an idea of how, but it's more general than this, it also works for infinite dimensional Hilbert space. So for a polynomial, we can do the following trick. Whenever we have a polynomial of the form C alpha x to the alpha, we can actually write P of E to be the sum C alpha, and then we use this tensor product notation E alpha 1 tensor E alpha, sorry, it should be alpha n. And the idea is that whenever we have an ideal in the free algebra, this corresponds to a subproduct system with prescribed fibers, and the fiber with label n is just the orthogonal difference of between the full tensor product and minus the subspace generated by the polynomial evaluated in the basis tensors. The correspondence works in the other way. So whenever we have a collection of subproduct system, we can find an ideal inside the free algebra that is an inverse to this map that I described above. Now, this correspondence implies that whenever we work with subproduct system, we are actually looking at the tuples of operator that satisfy some relations given by homogeneous polynomial. And this is related to other recent work by Popescu on the study of non-commutative domains. So this should serve you as a motivation as what happens when we look at the Drury-Alverson space over at analogs of the Drury-Alverson space, where instead of having commutative polynomials, we have now free algebra quotient by an ideal. Okay, now whenever you have a standard subproduct system of Hilbert spaces over the positive integers, we can consider the direct sum of all those Hilbert spaces that made up our system. And this resulting direct sum Hilbert space is what we call the Fock space. Now on this Fock space, we're gonna define operators that are just creation operators, and we're gonna do it in a way that is similar to what was happening for the compression of the D shift. So we take an element in our Fock space. So suppose you have an element in the Fock space that actually sits inside the fiber labeled by M. And then we take a vector psi in EK. We take the tensor product of psi with zeta. That's an element of EK tensor EM. And in general, EK tensor EM may not be one of the fibers of our subproduct system, but we do have a map, which is the iota star. It's the adjoint that of the map that we saw before that maps EK tensor EM into EK plus M. So in this way, we first shift and then compress down onto our Fock space. And now the Toeplitz algebra of the subproduct system E, which we denote by TE, is the smallest unital C-star subalgebra of the algebra of bounded operators on this Fock space that contains all these creation operators. So that satisfies the requirement that T psi belongs to this algebra for all psi in EK and for every K in S0. Now, this definition of Toeplitz algebra of subproduct system actually makes sense in a more general case studied by Chalit and Solel of sister algebras of subproduct systems of correspondences. So you should think, of course, there you should be more careful because you would have to require different condition on the correspondences that make your subproduct system. But for what I'm going to discuss in the rest of this talk, so the second half of this talk, it's you should have this definition for Hilbert spaces in mind. Okay. Now, as said, if X is a subproduct system of finite dimensional Hilbert spaces, we are in a very special situation, and there is a result that was proven by Wieselter in 2012 that the algebra of compact operators on this Fock space is actually included in the algebra of Toeplitz operators. So these allow us to define the Kuhn-Spinzer algebra of the subproduct system in a fashion that is very similar to how Kuhn-Spinzer algebras of correspondences are defined. We just say that it's a quotient appearing in the extension 0, maps to K over T, sits inside T, and then this quotient is called the Kuhn-Spinzer algebra. Now, this is an exact sequence of sister algebras, so it's natural to wonder whether this exact sequence can tell us, give us some K-theoretic information, and this is what I'm going to discuss in the rest of the talk. So I'll try to answer the question: what does this? Can we say something about the exact sequences that this extension of sister algebra induces? Okay. So we are going to restrict now our attention to yet another special case of this construction. So we're going to, as my title said, I'm interested in symmetries of sister algebras that come from the group SU2. So my starting point now will be a strongly continuous unitary representation of the group SU2 on a finite dimensional Hilbert space. Now, for every such representation, we define what we call the determinant of the representation. And this is the collection of those vectors that belong to the tensor power as tensor product of H with itself that are left unchanged by the diagonal action. sorry. So for every positive n, we consider an irreducible representation then, and then we know that irreducible representations are, well, if you're a physicist, they're labeled by half integers, but here I will consider them to be labeled by integers just by doing a shift. So for every n, we have an irreducible representation on an m plus one dimensional Hilbert space, and this n plus one dimensional Hilbert space is the symmetric tensor power of C2 with itself. So for that, we have an normal basis, which we labeled as EK, with k ranging from 0 to n. Now, whenever we have an irreducible representation of some Hilbert space H, and we have a unitary operator intertwining this irreducible representation with the irreducible representation rho n, then we can compute the determinant of tau, and this is a one-dimensional vector space which is spanned by this vector. So, okay, here you have v times of v because you're going back using this intertwiner, but this vector is an alternating sum of EK with of the tensor power of EK with n minus k times, well, there's this normalization constant. Now, the reason why I wrote down this determinant will be apparent later on, but if you think about what I said about the correspondence between non-commutative polynomials and ideals in the algebra of the commutative polynomial and subproduct system, you immediately see that here we have, there will be an underlying quadratic polynomial. Okay. Now, the way we construct subproduct systems from SU2 representation follows a sort of algorithm or an induction process, which is also reminiscent of some of the theory of quadratic algebras. So for every n positive, we start from a irreducible representation. As said, this irreducible representation we label n is the representation of SU2 on the n plus one dimensional complex space, which is the symmetric power of C2, the n symmetric power of C2. Then we take the determinant of this irreducible representation, that is a subspace of the tensor power of Ln with Ln. And then out of that, we construct inductively a subproduct system where E0, the fiber is 0, is just a complex number. E1 is Ln, so it's the space of our irreducible representation. And then Em is the orthogonal complement of some space inside Ln to the power m. And this is orthogonal complement of the sum of the spaces we get by tensoring Ln with itself and then putting D inside this tensor in all the possible ways. So if you know quadratic algebras, this is the way you define the various higher degree element in the quotient by a quadratic relations, but this is precisely what we're doing here. We're looking at Km as, this is not a direct sum, this is just a sum, as the span of all possible tensors of a certain form, and there is always a copy of the determinant inside those tensors, and it can either appear at the beginning or in the middle, or at the end. Now, we have structure maps that are induced by canonical identification of L to the power k plus m with L to the power k times L to the power m. And these maps are SU2 equivariant. So we say that the pair of subproduct system and structure maps actually forms what we call an SU2 equivariant subproduct system of finite dimensional Hilbert spaces, which means that we have a subproduct system of finite dimensional Hilbert spaces and we have equivariant maps at every step. All right, so this is our ingredient for the construction. To give you an example of what this construction covers, I'm going to go back to what we discussed before. So we start with the standard basis of T2. We take the fundamental representation of SU2 on C2, so the familiar one, AB minus B star A star. And then we look at the determinant of this representation. And this determinant is actually proportional to a specific vector, which is E0 tensor E1 minus E1 tensor E0. This is a vector inside the tensor product of C2 with C2. And you see from here that the determinant of this representation is actually the usual determinant of C2, which is the wedge product of C2 with itself. Now, if we do our procedure, the one I described before, so this inductive procedure, what we get and it follows from the Clash-Gordon theory of the representation of SU2, is that the fiber of our subproduct system, which I wrote here on the right-hand side, are actually the symmetric powers of C2 with itself. In particular, if you want to give a more even clearer description of what this space looks like, well, we simply use the orthogonal projection from the tensor into the symmetric tensor, and then the vectors that would be the basis of our EM are just a projection of E0 to the power k times E1 to the power m minus k. These are precisely the basis vector that you have in the Drury-Arveson space when you look at it as a symmetric Fock space. So the upshot is that when we when you apply our algorithm to an irreducible representation, we get a collection of Hilbert spaces that form a subproduct system. If we apply the algorithm in particular to the fundamental representation of SU2, what we get is the familiar Drury-Arveson space. But of course, we're interested in doing this for every under much generality. So let's look at what happens when we have a generally reducible SU2 representation. So we have this theorem. There's no name, but it's I should acknowledge Jens again. So for each k and m, there exists explicit SU2 equivariant unitary isomorphisms between the tensor product of ek with the m and the sum of Hilbert spaces, and we sum basically from k plus m, and then at each step we go down by 2, and we all go down until the absolute value of k minus m. Now, if you're familiar with the Clash-Gordon theory for SU2, this is precisely what happens in the case of the fundamental representation. Whenever you tensor two representations, you get that their tensor decomposes into this sum. But what we have here is that the fiber of our SU2 subproduct system, even if they are not irreducible representation, they still behave like they were. So they still obey these fusion rules. I know the word fusion rules is meant for irreducible representations, but we have fusion rules for fibers of SU2 subproduct systems. So in particular, we can have a look at the dimension of the fibers of our subproduct systems, and they satisfy a series of recursive formulas. So with D0, which is, as we know, E0 is the complex numbers, D0 is equal to 1, D1 is equal to n plus 1, which is the dimensional of the irreducible representation with the label n, and then the higher ones can be computed recursively with this formula. So we really can compute all the dimensions of this fiber of subproduct system, and this implies explicit SU2 equivariant unitary isomorphism between the tensor product of ek with the m and a certain direct sum. So you see also from here that the ek plus m sits inside the k tensor m, as we have because of having a subproduct system. Okay, so now starting from this subproduct system constructed from an irreducible representation, we can construct a Fock space. And we just take the direct sum Hilbert space, and then for looking at the orthonormal basis for the first fiber of our subproduct system, or if you want, for the Hilbert space on which SU2 is represented, we define a Toeplitz operator Ti, which is just a Toeplitz operator associated to EI. So if you want to write it in a familiar way, you just tensor an arbitrary vector in the fiber with label m, with EI, and then you use the adjoint of the structure maps to project down to the relevant subspace. In particular, these Toeplitz operators are SU2 equivariant because we can define an action of SU2 on them by saying that Gx on Ti by just giving you the Toeplitz operator associated to the vector that you obtain by acting with G on the vector EI. This defines a strongly continuous action on SU2 on the Toeplitz algebra T, and this action also descends eventually to the Kunz-Pimser algebra. Okay, this is our Toeplitz algebra. It has an SU2 action. Now let's see if we can say something more about this algebra. So for that we need to introduce some unbounded operators. And again, you should keep in mind what I said earlier about the Toeplitz extensions for spheres, because there was also a familiar unbounded operator, which was a number operator that was playing a big role. Here, instead, we define a different operator, which we call the dimension operator. So it is the closure of the unbounded operator on the algebraic Fock space that maps an element of the mth Hilbert space in our subproduct system to the dimension, to the same element multiplied by the dimension of the Hilbert space in which this psi lives. This is a positive operator, it's invertible, and it's inverse in an SU2 equivariant compact operator. If you want to do a sanity check, if you apply this to the fundamental representation, then the dimension operators equals n+1, where n is the number operator. So it's exactly that operator that was appearing in the commutation relations for the triplets algebra. Moreover, we also have another equivalent bounded positive and invertible operator, which is called phi, and this is a ratio of two successive dimensions. So if psi lives in EM, then phi acts on psi by multiplying it with the dimension of the space it lives in, divided by the dimension of the next space. All right, the reason why I introduced those two operators is because we were able to find the commutation relations for the tuplets algebra. So for every fixed integer and for every irreducible representation of SU2, we constructed a sister algebra generated by those n+1 tuplets operators, and they satisfy commutation relations. The first commutation relation is the one that comes from the determinant. So the alternating sum of products of Ti with Tn minus I is equal to 0. Then we have a relation between the Ti star and Tj and the adjoints of shifted operators. And this is consistent with the relation that was implying essential normality for the Algebra tuplets algebra. And then we have another sort of familiar relation, which is when we sum up Ti star with Ti, we actually get this phi to the -1. So it's an inverse of it's the inverse of that ratio of dimensions that we saw before. Now, if you plug in n equal to 1 in all of this, you get the T0 and T1. From the first one, you get the T0 and T1 commute because we only have two operators. From the second one, you get the essential normality of the tuplets operators in T2. And the last one just tells you that Ti star Ti is equal to 1 in this case. It's equal to a ratio of dimensions. But this recovers exactly the commutation relation that we had for the Algebra tuplets algebra. But this is there for every irreducible representation. So you should think of the Algebra tuplets algebra as a special case of our construction for the fundamental representation of SU2. Okay. Now, in the very last part of my talk, I want to talk about the K-theory and of the tuplets and of the Kunzweiser algebras of an SU2 subproduct system. Okay, so we construct, so the upshot of this section is that the tuplets algebra of our subproduct systems are always KK equivalent to the complex numbers, and they are so in an equivariant way. And this has consequences for the computation of the K-theory groups of the Kunzweiser algebras of our subproduct systems. So the way to show that is to construct, to show KK equivalence is to construct two maps that implement this KK equivalence. So let me start with a slightly more involved one. That we constructed a quasi-homomorphism from the tuplets algebra to the complex numbers. So we look at the Hilbert space direct sum of the Fock space with itself, and we construct two star homomorphisms that go into the bounded operator on F plus F. So the first one is just a diagonal representation. So we just represent X on each of the two copies. To construct a psi minus, we need to use the representation theoretical considerations. I'm not going to go into details here, but the idea is that we have an SU2 equivariant unitary isomorphism between the sum of EM plus 1 and EM minus 1 to EM tensor E1. And this we use to construct another SU2, another typo, NN. Use this to construct another SU2 equivariant isometry that now happens at the level of F tensor E1 and maps it to F plus F. The image of this map, WR, is F plus F. So it maps into the positive part of the Fock space direct sum with F. Using this WR, we can define the second star homomorphism in our quasi-homomorphism, which is just, we just take X, we tensor it with 1, and then we intertwine it with WR to get a map from F plus F to itself. Then we prove that the pair of a star homomorphism actually defines a class in KK0 TC, and actually it's a class in KK0 SU2 TC, because everything that appears in this quasi-homomorphism is actually equivariant. And now the proofs require several estimates about and commutators and differences. I'm not going to go into the detail, but they follow somehow from the dimension considerations that I gave before. So the fact that this the dimension of the fibers of this subproduct system satisfies certain conditions. Now, this is the somehow difficult quasi-homomorphism. The other one is the obvious one, is the canonical inclusion of the complex numbers into the Toeplitz algebra. This gives you a class in KK0 SU2CT. Okay, now what we do? Well, we prove that what we would like, which is that when we tensor, when we take the Kasparov products between these two classes in all the two possible ways, we actually get the identity on both sides. And our main result is indeed that the Toeplitz algebra of the SU2 subproduct system of an irreducible representation is KK equivalent to the complex numbers. Now, there is a easy direction, which is proving that I tensor with psi plus psi minus is equal to the identity on the complex numbers. And this just follows by looking at, well, this product is actually psi plus composed with I, psi minus composed with I. This gives you a quasi-homomorphism, and it's easy to see that this quasi-homomorphism is equivalent to the identity on the complex numbers. The other part of the proof is very involved, and it requires sometimes and lengthy computations. In particular, it relies on a homotopy argument, but we were able to show that when we take the tensor, the Kasparov product in the other direction, what we do is get a quasi-homomorphism that is homotopic to the identity in KK0 SU2 TT. The reason why we had to use this homotopy argument that is quite lengthy is that we don't have universal properties for our Toeplitz algebra yet. We do have commutation relations, but we don't know what the universal properties of Toeplitz algebras of general subproduct systems are. So in order to prove that this product here on the left is actually homotopic to identity, we had to explicitly intertwine representations of our Toeplitz algebra, and then get the resulting, prove that the resulting representations were actually homotopic to the identity. So this is a quite involved argument, and unfortunately we don't have these universal properties for this Toeplitz algebra. That will be a natural question and further development for this research line. But we do have this result. We do have the T and C are KK equivalent, and this has profound implications because we have this extension, the defining extension of a subproduct system, which contains contains the compact operators of the Fock module, the Toeplitz algebra, and the Kuhn-Spinzer algebra of the subproduct system. So in particular, we know that compact operators on some Hilbert space are always Morita equivalent to the complex numbers. Now we know that this algebra here is also KK equivalent to C. So the exact sequence that this extension induces can actually be simplified, meaning that we can use those equivalences to replace this K-theory group by the K-theory of the complex number, and those two K-theory groups by the K-theories of the complex numbers again. So let me show you the next step. Okay, this is a quite long identity, but this identity basically tells you what happens when you replace the K-theory of the compact operators with the K-theory of the complex numbers and the K-theory of the Toeplitz algebra with the K-theory of the complex numbers. Particularly, this tells you what the map in the middle is, so what the map between K0 of C and K0 of C is. And this map is an alternating sum of k classes. So we call this the Euler class of the irreducible representation. And this is the alternating sum of the identity on the complex number, the class of L, and the determinant of the representation. And now, because we're dealing with representations and because we're over the complex numbers, this can simplify further, and it's actually equal to 2, because these are both one-dimensional. And this is dimension, oh, there should be a bracket here, 2 minus n plus 1. Yes, there should be a bracket, I'm sorry. So we can simplify it further because we are in this Hilbert space case and we know everything about those representations. But what I want to stress is that we do get an exact sequence of K-theory groups, and the map in the middle is an alternating sum of 3 terms. Now, if you're familiar with Pimsner's construction, this is very similar to the identity gets, but in its identity gets just 1 minus the class of the bundle. Here, instead, we get, instead of 2 terms, we get 3 terms. Okay, so in particular, the exact sequence we have sort of recalls as a similar form to what what is called the Gisin sequence for sphere bundle. And of course, by using the name, I'm slightly cheating because there's no bundle here. There's just something that looks like a sphere, or that at least has a spherical symmetry. But the idea is that really this class that we have in the middle has a lot of resemblance with the Euler class of a vector bundle. This is here just a Euler class somehow of a representation. The other consequence is that in particular in this case where the coefficient algebra are the complex numbers, we get we get that the K1 of the complex numbers is trivial, so we get zeros at the beginning and at the end of our exact sequence. So in particular, we can compute the K-theory groups of our Kunz-Pimsner algebras of our SU2 subproduct system as kernels and co-kernels of this map in the middle. And because we know what this map in the middle looks like, then it means that we can be very concrete and get that the K0 group of our Kunz-Pimsner algebra is almost always a torsion group, and the K1 group is almost always 0. Now, the interesting cases, as you see, are the one for n equal to 1. For n equal to 1, we get ZZ. Well, that's not surprising because we already knew what extension we had. It's the extension of this 3-dimensional sphere. So we know that the K-theory of the 3-dimensional sphere is Z and Z. So we don't gain much, but that's a special case. All others have torsion. The one that does have a different flavor is the one we get for the triplet representation, the representation labeled by 2. And in that case, we get a sister algebra that has trivial K-theory groups, but is not the Kunz algebra O2. So this is basically the main result of our work. So the ability of constructing these new sister algebras from equivariant subproduct system, and the fact that we can compute their K-theory exact sequence and compute their K-theory group. And what I would like to stress is that the fact that this map has this form seems to be saying something about the subproduct system being a suitable candidate for understanding sister algebras with spherical symmetries. So let me summarize, give you some outlook on what I talked about. So I briefly told you that Kunz-Pimsner algebras were a model for circle bundles, and it seems from the evidence that we have gathered in this project that Kunz-Pimsner algebras of subproduct systems are suitable to encode a different type of symmetries, which are more spherical symmetries. So Kunz-Pimsner algebras came naturally with a U1 action. These Kunz-Pimsner algebras of subproduct systems, at least in the case we investigated, not only have a U1 action, they actually possess an SU2 action. And this SU2 action is already there at the level of the Toeplitz algebra, and it descends to the quotient. And the resulting exact sequence also manifests this spherical symmetry because they have this Euler class, this alternating sum of classes. We have several open questions that are still left open, and one of the most pressing one concerns the universal properties of our subproduct system, sister algebra. The reason why this is important also has to do with the homotopy argument. because in the proof that, if you're familiar with the proof of KK equivalence that Pimster shows in his paper there, the universal properties for the tuplets algebra are used widely, but here we don't have such universal properties, so we have to resort to this complicated homotopy argument. The other question that we would like to understand is what happens when we extend our results to reducible representation of SU2, because in that case, our determinant won't be one-dimensional anymore. And this will mean that we will have to deal with several other relations in the resulting algebras. And of course, well, it will be probably one of the ultimate goals to be able to extend this construction to C-star correspondences with SU2 symmetry or an SUN symmetry to get different type of C-star algebras. Here, everything is over the complex numbers. We're dealing with K-theory of complex numbers. So there's not much room for wild behavior there. But if we would have a different coefficient algebra, then the floor is still completely open. And with this, I would like to thank you all for your attention and conclude my talk.
Thanks very much. Applaud. All right. So, are there questions?
Sorry, very stupid one. At the very last, the very last thing that you said before the outlook was that an algebra looking like the Kunz algebra O2 was not O2. Why was not O2?
No, we're okay. That's my conjecture. I don't think this algebra is simple, but I was not able to prove that it's not. So, yeah.
Okay.
It still needs some work, but I suspect that this algebra, given the commutation relation that we have in the tuplets algebra, doesn't seem to be the Kunz algebra. But
okay, thanks.
That's a conjectural.
I had a question where, so you seem to be generalizing, say from let's say you go from U1 to SU2, and then you take into account all irreducible representations. But why would you do that instead of going to say SUN and stick with the defining representation?
Well, this is actually done. So there is some work by Andreas Andersson where he constructs subproduct systems with compact group symmetry, but he constructs one subproduct system for every group, and he always does it for the fundamental representation. But what we were doing here is we're indeed looking at what happens when you start from a different SU2 representation. And somehow, well, we had sort of this analogy that this should be sort of Kunz algebras, but in a different way, like the Kunz algebras appear in Pimster's construction.
Okay, there's Nikolai Ivankov with a question.
Yeah, I just had a question. I haven't really understood. So why don't you have this universal property, or whether you can construct it from with some other means? Could you please?
Well, I think we have. Well, I mean, let me go back to my slide. So we do have commutation relation in our tuplets algebra, but at the moment it's oh, okay, I highlighted this. It's not so transparent to me what universal properties they should come from. So it's quite an involved problem that has it's been addressed by several people in the years. Of course, we are working here with a very special case, but unlike what happens in the Kunz-Pimster case, where when you take the product of a TI star with TJ, and then this is equal to the acting with the inner product of those vectors. Now this is completely lost here, so we don't have it anymore. We suspect that there should be some SU2 symmetry playing a role in the universal properties, but we haven't been able to observe this in a productive way. So yeah, so that's my answer. So the upshot will be, yeah, maybe over time this will be transparent, but at the moment it's not really transparent to us what the candidate universal properties could be.
So in general, I think it's a wide open problem. If you have a subproduct system, you can construct the triplets algebra, but you don't know whether it's described by some universal properties.
Yeah, I see that Baruch Solel was here, so if he wants to add something to that, he will be welcome. But yeah, indeed, that's a problem that was raised, well, probably 11 years ago already, and still there's no clear answer to what and if there are any universal properties, as far as I am aware. Okay.
There's a question in the chat, or maybe a remark that you could maybe something. If there's some research, can you read it? Or?
I need to find the chat.
So I can also tell you. It's about the question is if there is research in the case that the Cantor set, rather than the circle, is the boundary of some non-commutative space.
Oh, that's a good question. I don't know the answer to this question actually.
Okay.
Yeah, I'm sorry, but yeah, there is, but at the moment it doesn't occur to me. But actually, yeah, so here we had S1 and S3 and S2D minus 1. So all the spheres is boundary of some non-commutative algebra. But I am not familiar with this.
Anything else? Then, if not, we thank Francesca again.
Thank you. I'll stop my screen.
Yeah.
Okay.
And we meet again next week, I guess, with Jens. So we'll continue on I guess on a different.
I don't think so. Yeah.
All right.
Okay.
See you then. See you
Thank
next
you.
week. Thanks a lot, Francesca.
Bye-bye. Thank you. Bye-bye.
Bye.
Bye-bye.